Hello Math 2 and welcome to week 13. It's a very exciting time because this is the last new thing we're going to do. Next week, week 14, is just going to be review. So the last idea is called the definite integral. And if you start with a very basic problem, let's say you've got a function y equals 3. So it's hitting the y-axis right here at 3. And then it's a horizontal line. And then on the x-axis, we're going to go from 1 to 5. And then find this area. So that right there is just a rectangle. So you just need to know what's the base. So that would be 5 minus 1. So area for a rectangle is just the base. 5 minus 1, so that's a length of 4. And then the height is 3. Area equals 12. And if it was in feet, that would be 12 square feet of space. All right, well, where's the calculus? Here it comes. Now take this function, y equals 3, and find the antiderivative of the function 3. And it's implied that the variable is x. This down here is the x-axis. And I had it go from x is a 1 to x is a 5. So I write that on the integral symbol and say, find the integral from 1 to 5. So when you find the antiderivative of 3, that came from the derivative of 3x. So the derivative of 3x is 3. So the antiderivative of 3 is 3x. Now I'm done with the integral symbol, so I don't write that anymore. Now I just write a straight line saying x goes from 1 to 5. And now I just need to plug in the numbers 1 and 5 for x right here. And it starts with the top number. So it's going to be 3 times 5. And then you subtract, just like in here I subtracted 5 minus 1 to get this 4. 3 times 1. So that's going to be 15 minus 3, and 15 minus 3 equals 12. We'll get the same answer. So turns out that antiderivatives, even though they're the opposite of a derivative, can actually tell you the area under the curve. That amazing fact is known as the fundamental theorem of calculus. Okay, now let's do another example. And again, I'm going to start with some geometry and then do the calculus. Oops, that wasn't on the screen. Now it's on the screen. All right, suppose that you have this function that goes right through the middle of the x and the y-axis. That would be the function y equals x. And then drop a perpendicular line down to the x-axis. And let's say that this goes from x is a 0 to x is a 4. Then find this area. Well, that right there is a triangle. So the area of a triangle is 1/2 times the base. And the base is a length of 4 times the height. Well, if x equals 4 here and you plug it in, that means y equals 4 as well. So that means this length is 4. That means this length is 4. So the height is 4. So 4 times 4 is 16. If you cut that in half, it's 8. And then if this was in meters, then that would be 8 square meters of space. So take this function and find the antiderivative of x. And then the x values go from 0 to 4. So it goes from 0 to 4. And with this one, I could say, well, that's x to the 1. So if you add 1 to the exponent, that's going to be x to the 2 over 2. So there's the antiderivative, which seems like it has nothing to do with area, but just wait. So then I just put the straight line saying I've found the antiderivative, and now I need to evaluate it from 0 to 4. And remember, you always start with the top number. So substitute the top number, that's going to be 4 squared over 2, and then minus, now use the bottom number, 0 squared over 2. And of course, this is just going to be 0. This is going to be 16 cut in half, and that equals 8, which is the same answer. So the antiderivative can tell you the area of the original function. All right, for these next few, I'm not going to draw the graph. It's just going to be find the antiderivative. So for example, number 3. So find the area under the curve as x goes from 0 to 1 if it's the e to the x function. So the derivative of the e to the x is e to the x. That means the antiderivative of e to the x is also just e to the x. And then evaluate from 0 to 1. So substitute the top number, that's going to be e to the 1, minus, substitute the bottom number, that's going to be e to the 0. And then this one's going to be a decimal answer, so I'll go ahead and use the calculator. So second, and then e is over here, e to the 1, and then minus second e to the 0, and it equals an area of 1.718. For example number 4, how about if you're finding the area under x squared plus 2, which is a parabola, and then have it go from -1 to +1. So right here, add 1 to the exponent, that's going to become x to the 3, and then divide by that 3. X to the 3, divide by 3. And the antiderivative of the number 2 is the function 2x. I guess I didn't need a red pen right there. Okay, so there's the antiderivative. Oh, and by the way, when we do antiderivatives without numbers, you do need to put a plus c at the end. But when you have numbers, you just get a number at the end. There is no plus c. So now evaluate from -1 to 1. So substitute the top number first. That's going to be 1 cubed over 3 plus a 2 times 1, and then minus. When there's only one number, you can just say minus that one thing. But this has two things, so I should put parentheses because the minus applies to both of them. And then it's going to be -1 cubed over 3 plus 2 times -1. So this, sorry, I'm adjusting my light, so trying to get rid of that shadow, Okay, this is going to be 1/3 plus 2. And then this means 3 negatives in a row, so that's negative. But then with this, it's going to become positive. So then plus a 1/3. And this right here will be -2, but with this negative, it now becomes a positive 2. So that means we have a 2 plus 2, so that's going to be 4. And then a 1/3 plus a 1/3 is 2/3. So you could say it's 4 and 2/3. And then on to example number 5. There it is. Find the antiderivative from 1 to 2 if it's 1 over x dx. So what's the antiderivative of 1 over x? Well, I seem to remember the derivative of natural log of x is 1 over x, so that means that the antiderivative of 1 over x is the natural log of x. And now just evaluate from 1 to 2. So that's going to be natural log of 2 minus natural log of 1. And that should equal a 0.693. Let's see. Natural log of 2 minus natural log of 1. So that equals a 0.693. And for example number 6, how about if it is integrate from 0 to 5, and then it's the 10th root of x. So for this problem, the first thing that I would do is rewrite this as x to the 1/10th power. So replace the radical with a fractional exponent, x to the 1/10th. And then add 1, and 1/10 plus 1 will be 11/10ths. 1/10 plus 1. If you go to math and ask it to make that a fraction, that is 11/10ths. So I then need to divide by 11/10ths. So this is going to be x to the 11/10ths. And then this, when you divide by a fraction, you need to invert and multiply. So it's going to be times 10 over 11. And then evaluate from 0 to 5. So it's going to be 10/11ths, and then 5 is raised to the 11/10ths minus 10 over 11, and then 0 is raised to the 11 over 10. And since this is a 0, it contributes nothing to the answer. So I really just need to figure out how much this part equals. So it's a 10 divided by 11, and then the 5 is raised to the 11 divided by 10. So that means that the final answer is 5.339. And now some that use U substitution. So for example, number 7, using U substitution. Integrate an x times x squared plus 5 if that part's raised to the 7th. So I'm going to use U substitution, and I'll let U be what's ever inside the parentheses. And the last part I need to do is the numbers. I'll have it go from 0 to 1. So using U substitution, let U equal the inside part, x squared plus 5. And now find the derivative. So the derivative of U equals, the derivative on this side is just 2x. And with U substitution, technically you're supposed to say this is du divided by dx, and then you multiply that dx onto the other side. So this part says we have x dx, and this part agrees, yes, we also have x dx, but there is no 2 in the original problem. So I need to multiply both sides by 1/2 so that this side just says x dx. And now this matches the problem, so now I can do the U substitution. When I do, I'm going to take this 1/2 and just factor it out front. And then it's going to be integral. And then when I replace the x dx with 1/2 du, so the 1/2 can go here and the du can go here. And then this is the u, and it's raised to the 7. And then do the antiderivative. Notice that I did not put the numbers 0 and 1 on this because that's for what x equals, that's not for what u equals. So I'm going to finish this problem. When I'm done, I'll replace the u with this x squared plus 5, and then I'll put the 0 and the 1 back once I'm back to x's again. But for now, I just leave off the 0 and 1. So it's a great time to use the red pen. Add 1 to the exponent. That's an 8, and then divide by 8. So this I could also factor out and just move it over here so that on the bottom it's now going to have a 16. So it's 1 over 16, and then u to the 8. And like I said, usually with antiderivatives we do put a plus c, except we're going to have numbers to plug in, so there is no plus c. All right, now replace the u with the x squared plus 5. So this means that it's 1/16 of x squared plus 5 replaces the u, and then the 8 power is still there. And now that I'm back to x's, I'll now put the 0 and 1 back. So put the straight line, have it go from 0 to 1. So finally that is 1/16, and then substitute the 1 in there, so that means it's going to be 1 squared plus 5 to the 8th power, and then minus 1/16, and then 0 squared plus 5 is to the 8th power. So I'm just going to simplify this a little bit before I use the calculator. This is a 6 raised to the 8th power. And this is a 5 raised to the 8th power. And what is that final answer? So I've got 1/16, and then there's a 6 raised to the 8th power, and then minus this 1/16, and then a 5 raised to the 8th power. And then I'm just double checking that I typed everything in. All right. So the answer is 80,561.938. And of course this number is so big because when you square something, that makes it bigger, and then when you raise it to the 7th, that makes it even bigger. So that's the reason the answer was so big. And then another u substitution. So for example number 8, if you integrate an x squared over an x cubed plus 9, sorry about that, was a little bit off the screen. And then let's just keep it simple, we'll go from 0 to 1. So this is another u substitution, and when you have a fraction, it's a good idea to try let u equal the bottom part, x cubed plus 9. And now take the derivative on both sides, so it's going to be du equals 3x squared is the derivative, and then times dx. So this one has x squared dx, this one also has x squared dx, but this one does not have this 3, so I need to multiply both sides by 1/3. And now it's ready for the u substitution. And like last time, this fraction, I'm just going to factor it out. And then the top part right here gets replaced with the 1/3 times du. So the 1/3 can go on the outside, and then the du can be right here. And then this bottom part is the u. So basically it is 1 over u. And the antiderivative of 1 over u, that's the natural log. So the 1/3 can stay there, and then it's going to be the natural log of u. And again, I don't plug in any numbers, and I don't even write down the numbers until I'm back to this being x. So this, when you replace the u, is going to be 1/3 the natural log of x cubed plus 9. And now that the numbers are, excuse me, the x is back, now I'll put the numbers, evaluate from 0 to 1. So this one is 1/3 natural log, and then 1 gets cubed plus 9, and then minus 1/3 the natural log, and then 0 gets cubed plus 9. And I can simplify this one a little bit before using the calculator, because this is going to be a 1 plus 9, so that's 10. And this is just a 9, so minus 1/3 natural log of 9. And how much is that? So that's a 1/3, and then the natural log of 10 minus a 1/3, and then the natural log of 9. Make sure I typed everything. Okay. So the answer is very small. It's just a 0.035. And then if you're wondering, is there a way we could check this on the calculator and see if this number is right? Well, you can. So what you can do is go back to the original problem and graph that. So this is, clear this out, x is squared gets divided by x is cubed, and then move over plus 9 and put that in parentheses. And since the limits are 0 to 1, I'm going to change the window. And I don't want to go exactly from 0 to 1. I want to give a little bit of extra space. So I'll go from -1 to 2. And I don't know what the y values are, so I'll just leave them as -10 to 10. And then graph. And now I can see why the answer is so small, because that is a very short function. So maybe if I have the y values go from -0.2 to +0.2. Can we see it better? Yeah, I could see it better. That's better. And then we're finding the area from 0 until 1. So we're finding the area, that area right there. And you can have the calculator check your answer if you go second calculate. And it's number 7 that integrates. And the lower limit is 0. And then hit enter. And the upper limit is 1 and hit enter. And then it says that the answer you should have gotten is 0.035. Très bien. So now this one even deserves a little smiley face. Okay, so there is one more idea that we need to do. This is example number 9. All right, suppose you have this function, y equals -x squared plus 5x. And that is a parabola. Go to y equals, clear this out, -x squared plus 5x. And then I'm just going to go back to Zoom standard. And it's a parabola. And I'm going to be talking about going from 0 to 5. Trace, if you plug in 0, it's hitting the x-axis. If you plug in 5, it's hitting the x-axis. So if we want to know the area between the x-axis and that parabola, then integrate. So integrate from 0 to 5, and then it's -x squared plus 5x times dx. So if you add 1 to the exponent, that's going to be a 3, and then divide by 3. So the first one is going to be negative x to the 3 divided by 3. And for the 5x, its exponent is a 1, so if you add 1, that becomes a 2, and divide by 2. So the next part's going to say plus 5x squared gets divided by 2. And then evaluate from 0 to 5. So when you substitute the 5, first of all, this is going to be negative 5 cubed over 3. And then this is going to be plus 5, and then substitute a 5 in here, so that's going to say 5 squared over 2, and then minus. When you substitute a 0, 0 cubed is 0, so that's going to be minus 0 over 3. And when you substitute a 0 right here, that's going to be 0 squared is 0, times 5 is still 0 over 2. So in other words, this is going to contribute nothing to the answer. So I only need to know what this part is. So that's going to be negative 5 is cubed, and then divide that by 3. And then it goes plus the 5, and then 5 is squared, and then that is divided by 2. And so the answer seems to be 20.833. And I can go back to the graph and check and make sure that I got it right. So I can go second, calculate, and then use number 7. The lower limit is 0, so start at 0, and then hit enter. The upper limit is 5, and then hit enter, and then it will shade the area, just like I did. And it says you should have gotten the answer 20.833. All right, that's good. Now for the new part. What about if it's the integral from 0 to 5 of the exact same problem? And then divide by 5 minus 0. So we don't have to redo the whole problem because I already know that the integral equals this. And then you take the length of the interval, so from 5 to 0, that's a length of 5. So if you subtract them, that finds the length of the interval. So basically, if you take 20.833 and you divide by 5, then what does that equal? So take the 20.833, and if you divide by 5, it equals 4.167. And then what does that mean? Well, basically, when you are doing this, you're adding up all of the area, and then you're dividing by the length of that interval, so you're actually finding the average value of the function. So this is the average value of the function. So if I go back to the graph, and I'm going to regraph it to sort of zoom in just on that part. So I don't need anything over here. I don't need anything over here. So if I have it go from 0 to 5, and then from, say, 0 to 10, let's see if I can see it. And I don't really need this space up here. So that is a height of 6. So I'm going to tell it go to a height of 7, just to zoom in on this part of the graph. Just to zoom in on this part of the graph. Okay, for the average, I got 4.167. So if I graph that as a function, y equals 4.167, then this is the average of the function. So basically half of the time it's below that line. So these two parts, half of the time it's below that line, and half of the time it's above that line. So this y equals 4.167 is the average.